Okay, hi everyone. Welcome to the pre-recorded lecture for Class 6. Last week we spoke about parallel spaces, isometric spaces, oblique spaces, and axonometry. This week we're going to be looking at perspective spaces, linear perspective, 1 point, 2 point, 3 point perspective, and the illusions that these can create and the history of where these systems came from, how they developed, and what sort of symbolic meanings perspective systems give us. For this week, you should have watched the Class 5 Blender exercise online and hopefully uploaded some rendered animations to Moodle or preferably to the YouTube channel before class. Then at the beginning of class, I'd like to review some of the images and videos you've made. And then we will discuss this week's lecture, which is perspective spaces. This will be followed by a student-led discussion of section 1 of Erwin Panofsky's Perspective as Symbolic Form. Then we will discuss some new drawing and perspective Blender exercises, as well as the upcoming theory presentations. So to remind you from last week, the Blender exercise was on rendering and exporting animations. So you should all have completed the bouncing ball animation and exporting exercise, as well as animated something from the parallel space scene that I made for you and uploaded onto Moodle. So hopefully I can view these on the Spatial Practice YouTube channel. Okay. So moving on to the lecture, this week we're talking about perspective spaces, and towards the end of the lecture we'll come back to this animated GIF I have on screen right now to discuss what it is, how it works, and how it relates to some of the questions about perspective that come out of the reading for this week. So the reading that this lecture is based on is section 1 of Erwin Panofsky's Perspective as Symbolic Form from 1927. Panofsky was an art historian and a proponent of a form of reading art called iconology. Panofsky encouraged a reading of art that sought to synthesize the detachment of Russian formalism with the sort of contextual awareness one gets from historical materialism. Now, to unpack that a little bit, when we talk about the detachment of Russian formalism, we're talking about aesthetics, and we're talking about a way of looking at art that partly derives from Immanuel Kant, and looking at art in terms of how the physical artwork generates experiences for the viewer, and what systems do we have to understand how the physical properties of an artwork can affect the viewer. Whereas historical materialism is looking at the social and historical context of an artwork. Who was the artist? When were they working? What was happening in society at the time, politically, technologically, philosophically, and how did these things shape the meaning of the artwork? Panofsky proposed 3 levels of art historical meaning. The first was the primary natural subject matter of the work. The second was the conventional subject matter, its iconography. What did it visually symbolize? And the third was the tertiary or intrinsic meaning, or the iconology, its historical context, its material context, what was happening in the world around this artwork. If you read the introduction section to Perspective as Symbolic Form, Christopher S. Wood gives a fantastic account of the tensions between philosophy and philology, which operate in Panofsky's attempt to create an art historical system for analysing the meaning of artworks. So just some background on the discussion of perspective that we find in the reading this week. Panofsky references quite a lot the difference between angle perspective and linear perspective. When he says angle perspective, he's talking about spatial systems that existed in European painting before the invention of linear perspective. And Panofsky certainly doesn't say that linear perspective is more realistic. What Panofsky wants to say is that these ways of drawing space had different intentions and different meanings. In the angle perspective from the 15th century image on the left, Panofsky would say that this image allows us to see many different sides of buildings and many different scenes that one person should never be able to see at any one time. It gives an overview of the world that linear perspective does not allow. In linear perspective, every object in the scene obeys the rules of the mathematics of perspective, rather than turning to face the viewer out of a kind of convenient revealing of the world. Linear perspective does the opposite. Linear perspective gives a mathematical system, and it gives a mathematical context for every single object and how it can fit into this world. And as we will discuss after this lecture and in our live session, Panofsky attributes very different meanings to these types of spatial systems. So let's have a look at some of the leading intellectual thinkers that led to the development of linear perspective. First of all, we have Filippo Brunelleschi. Brunelleschi was a 14th and 15th century pioneer of Renaissance architecture and one-point linear perspective. Brunelleschi's experiments relied on a device that created a fixed monocular point of view. What that means is looking with one eye without moving, fixed, not moving, monocular meaning one eye. And Brunelleschi used this device to draw objects on a grid. He also used mirrors to test the accuracy of his drawings. And again, if you go back to Christopher Wood's introduction to perspective as symbolic form, he gives an excellent account of the varying relationships between optical observation compared to the philosophies of representation that were occurring in the Italian Renaissance at this time, relevant also to the philosophies of Immanuel Kant and the thing in itself being the object as it exists versus the thing in perception, the object that we can perceive. And Wood situates all of these discussions of perspective in this paradox, that there is a world that we take to exist, but then there is a world that we can perceive via our bodies and also via the concepts that structure our way of thinking. And this is where Christopher Wood helps give some context to what Panofsky is writing about. The second pioneer of linear perspective I want to introduce is Leon Battista Alberti. Alberti was a 15th century Italian Renaissance author, architect, poet, priest, linguist, philosopher, and cartographer. Alberti wrote De Pictura, which was a treatise on painting, colour, form, and perspective. And you'll see here in some of Battista's diagrams, or Alberti's diagrams, sorry, that a lot of the science of how perspective drawings work are exactly the exercises that I'm going to be introducing to you in the second half of this lecture. The third person I want to introduce is Albrecht Dürer. Dürer was a German artist and theorist of the German Renaissance. He wrote 4 books on measurement, instructions for measuring with compass and ruler, highly influenced by Euclidean geometry. And in the image I've got on screen here, you can see this device that Dürer is representing sort of illustrates what we're talking about using a fixed monocular point of view. What's happening here is that the artist has this sort of needle that he lines his eye up with, and he views the world here, the world represented by the naked woman, and he looks at where this view intersects with the grid points here, and then he copies these intersections down onto his gridded piece of paper. And, you know, there are a number of fascinating symbolic ways to view this image. On the one hand, what Dürer has done is he's created a metaphor for what the science of perspective does. It compresses the world into 2 dimensions, and these 2 dimensions are then transferred onto the image. And by having these 2 windows here, we sort of have that window effect of the landscape. The landscape is also a compression of the world onto a 2-dimensional picture. The other kind of interesting thing of this image, of course, is that Dürer is symbolically representing the world, the subject as the woman, the object. The object is the woman, and the perceiving subject as the male scholar. And this creates a kind of interesting dynamic that's probably highly representative of its time, but also, philosophically, it points out some interesting ideas that if we consider perspective as, I guess, a sort of conceptual framework or even a conceptual barrier to experiencing the world as it is, we could look at Dürer's image and say, okay, well, if Dürer is saying that the world can be perceived through perspective, we could also see these bars as a prison that separates this individual here from the world. So to me, it's always been a very fascinating image, Dürer's representation of perspective, because it can be viewed in a number of different ways in terms of the relationship between rational systemic thinking and the world as it is, here personified by the male scholar and the naked female form. Okay. The final person I want to introduce is René Descartes. Descartes was a 16th and 17th century French philosopher and mathematician and scientist. Relevant to us here is Descartes' development of analytical geometry, and this is where algebra and geometry are brought together, which also influenced the development of calculus by Isaac Newton and Gottfried Wilhelm Leibniz. And you should be able to think back to the Cartesian plane that you would have experienced in high school algebraic geometry. And the Cartesian plane is also, where we find the fundamental mathematics behind 3D graphics, behind the way that Blender is able to display three-dimensional forms on the two-dimensional screen, and also behind all of the 3D graphics engines that we use in computer games, computer-generated images, etc., etc. Okay, so now I want to move on to a demonstration of how perspective drawing systems work. And you can refer back to this demonstration, both in this video and in the notes that I'll upload, for how to use perspective drawing yourself to construct architectural objects on a physical piece of paper drawing. Or in this case, I made these images just on my computer. Okay, so if we're going to draw a one-point perspective image, the first thing we're going to do is we're going to make a one-point perspective grid that will allow us to place objects in the scene, and it will also allow us to scale objects within the scene. So my demonstrations here are quite simple, but hopefully they should give you the basic principles from which you can then expand into more complex forms. Okay, so one-point perspective. We start by drawing a horizontal baseline here with evenly marked spaces. Then we draw a second line, which is the horizon line. And the horizon line would be, if you think about standing outside and looking as far as you can see, the horizon line will be where the sky meets the ground. The vanishing point here I've placed in the middle of the horizon line. And then there are these 2 points here called distance points. And with the distance points, from the evenly spaced markers, simply just connect each marker up to the vanishing point. Then connect each distance point with the markers on the baseline. And if you connect all of these up and then look at where the distance points cross with the points that are going to the lines going to the vanishing point, use these points of intersection to draw a grid. And that grid should give you the perfect spatial recession of a square grid in one-point perspective. And once we have this, we can start to draw objects in space with the correct scale to the one-point perspective system. And as you'll remember from last week, there are a few things to notice. The first is that the square face here on this tetromino, the Tetris shape that I've drawn here, the square face here is facing the viewer. And that means that this shape here is actually a perfect square. So what I've done is I've connected up these grid points on the base. I projected up a perfect square here. And then I simply traced these lines of the top to the vanishing point. Then I projected out horizontally another square, projected to the vanishing point, and so on and so forth. The only difference here with this turquoise shape is that I raised the shape up off the ground to show you that the higher the form gets, the less that we see of the top of the form. And if I'd moved this shape up even higher and drawn it, we would no longer be seeing the top of the shape, we'd actually just be seeing the bottom of the shape. And then just to give you an idea of what these shapes are, so that's not just a mess of lines, I've just done some basic three-tone shading where on the top I've used a light tone, the faces that are facing us, the viewer, I've used a mid-tone, and then for the remaining faces I've used a shadow tone, just to give you an idea of what these shapes are separate from all the construction lines. So moving on to two-point perspective. Two-point perspective is where we have two vanishing points. To create a two-point perspective grid, we again draw a horizon line with two vanishing points here. So these are going to be vanishing points now, not distance points. And then this red dot here is going to be the corner of the grid. Now I'll show you how this works. On that red dot, I'm drawing a line through the dot, and again, I'm going to mark out evenly spaced points on either side of the original dot, which is here, and these will determine the number of squares that we're going to end up with on the grid. And then, much like last time, this time we're using the vanishing points themselves. We're just going to rule up lines from the left-hand vanishing point here to all of the marker points that are on the right-hand side of the corner of our grid. And then the same with the right-hand vanishing point. I'm ruling lines that connect to all of the markers on the left of the original grid corner. And then again, I'm just locating some architectural objects on the ground or above the ground, above this grid. So here, I've just drawn a cube, but you can see that unlike one-point perspective, none of these faces are squares on the paper anymore, and none of them are facing us. And if we project up here, this shape I've made, now that it's above the horizon line, we're no longer seeing the top of the object. Instead, we're seeing the bottom of the object, and that's because it's above the horizon line. And the horizon line symbolically stands in for where our eyes are. It's the eye level of the scene. Okay, so just a little bit more detail for two-point perspective. We can go to far more depth of calculation with algebra and Blender. We can do very sophisticated calculation. But for the sake of drawing, we can divide our spaces in interesting ways. So, for example, if I'm going to draw this building here, and I want to know where halfway through this plane is, halfway will not be the middle of this shape, because in perspective, things that are closer to us are larger and further away are smaller. So therefore, one half of this building has to be longer than the other half. So to bisect or cut in half one plane in two-point perspective, all we have to do is draw the diagonals of that shape, and where the diagonals intersect, that gives us the halfway point of the perspectival plane. And if we want to divide it in thirds, we can take one diagonal here of the whole shape, and then we can use, if we had cut it in half here, we can use the diagonal of the half and the diagonal of the smaller half, and where those sub-diagonals cut the main diagonal, we will find the way to trisect this shape. Now, you might want to watch that a few times to know what I'm talking about, but I'll also upload these slides to the notes for you to look at in your own time. But the benefit of being able to do this, as you can see here, is that now I can cut up this building into, some sort of building that has 3 doors that are evenly spaced according to the recession of perspective, so that the spacing is sort of worked out correctly. Okay, moving on to 3-point perspective. So 3-point perspective is something that you might be more familiar with in, say, comic books. It's very common. 3-point perspective is used to exaggerate height. So to create a 3-point perspective space, we can pretty much just recycle our 2-point perspective grid down here, but we're adding a very high vanishing point up here, much above this kind of original horizon line, which we're sort of going to discard. And the high vanishing point, instead of our verticals being parallel, now our verticals are also converging to this high vanishing point up the top, such that if I shade my form here, we can see that we've got an exaggerated recession in height, which gives us the impression of standing at the bottom of a tall building looking up to the top, where we would see that spatial recession. And we can, invert this principle, of course. We can have our regular 2-point perspective grid up the top, and we can put a very low vanishing point down here, and do the same thing, project our lines down from the grid such that our vertical lines are now converging to the lower vanishing point. And this would give us the perspective of being on top of a tall building, or higher than this tall building actually, if we can see the top, looking down to the ground. So therefore the ground of the building looks much smaller than the top of the building, which is closer to the viewer. And if you want to go any further in looking at how perspective works, I'll put these 2 websites in the description of the video, and they've got some fantastic perspective drawing resources for you to look at. So if you connect together the lecture from last week with the lecture from this week, we've pretty much covered all of these systems here. Last week we looked at parallel spaces, particularly the isometric and the oblique. And now we've just had a very quick run through of perspective projections, 1-point, 2-point, and 3-point. And the reason I want to dwell on this slide again is that what this slide should show us is that all of these different drawings of this, this blue cube here, are different ways of getting around a problem. And the problem is how to remove one dimension of space. We have a 2-dimensional piece of paper or screen, and we have a 3-dimensional object as we experience it. And what I'd like to emphasize is that according to, I'd say, Panofsky, and certainly my own opinion also, we could never really consider any of these 2-dimensional solutions for 3D space as more realistic than others. I would say that they have different functions, because what is lost every time is the 3rd dimension. But the way that the 3rd dimension is lost, we might describe as the rules of the system. Each of these systems has a different way of removing the 3rd dimension, and each time it usually has a different purpose. And in our discussion of Panofsky's perspective as symbolic form, hopefully we can go into a little more of the historical context of why this was happening at the time. Excuse me for a moment. Okay, so I want to move beyond Panofsky's text a little bit and look at where the development of perspective took us to the development of photography. As you could see in that image from Dürer that we looked at previously, the projection of the man with the needle looking through the grid at the naked woman was almost a human description of the mechanism of a camera. Leonardo da Vinci's use of what's called a camera obscura is also part of this process of using the science of optics and almost a form of automation to, in some ways, remove the hand of the artist and to introduce a mechanism for creating images. And this introduces some fascinating questions for what is realism, what is representation, and also what is perception. In a fabulous essay by André Bazin called The Ontology of the Photographic Image, Bazin talks about the development of photography in a similar way to how Panofsky talks about the development of perspective. For Bazin, photography overcame subjectivity in a way undreamt of by painting, a way that could not satisfy painting, one which does not so much defeat the act of painting as escape it altogether by automatism, by removing the human agent from the task of reproduction. Bazin also writes that photography and the cinema are all discoveries that satisfy once and for all, in its very essence, our human obsession with realism. Only a photographic lens can give us the kind of object that is capable of satisfying the deep need man has to substitute it for something more than a mere approximation, a kind of recall or transfer. The photographic image is the object itself, the object freed from the conditions of time and space that govern it. However, Bazin also recognizes that the object that is captured by photography, and here I really want us to consider photography as almost the inevitable outcome of the science of perspective. And for Bazin, what we get with photography is not the object itself, but some almost unreal counterpart from it. And Bazin was, in his essay, looking particularly at surrealist photography. Bazin writes, wherefore, photography actually contributes something to the order of natural creation instead of providing a substitute for it. The surrealists had an inkling of this when they looked to the photographic plate to provide them with their monstrosities, and for this reason, the surrealist does not consider his aesthetic purpose and the mechanical effect of the image on our imaginations as things apart. For him, the logical distinction between what is imaginary and what is real tends to disappear. And on the right-hand side of the screen here, I've got a famous photograph by surrealist artist Dora Maar. And this was a controversial photograph at the time because it looks like something that is monstrous or couldn't possibly be real. And what Bazin is saying here is that, yes, the invention of photography was the ultimate automation of the science of perspective. Arguably, Blender is, in fact, the ultimate automation of the science of perspective. But photography, instead of creating a substitute for reality, photography created its own parallel reality, this kind of surrealistic other reality. And so now I want to return us to this animated GIF that I started the lecture with, and you might be familiar with this effect from various films. This is called the Dolly zoom, or the Vertigo effect. And the Vertigo effect is essentially a very surreal, quite disturbing manipulation of the science of perspective. The Dolly zoom or Vertigo effect does not require any special effects. It simply uses the science of perspective to create a surreal illusion that disrupts our sense of space and balance. Typically what happens is the foreground element, in this case we have this concrete block, it remains relatively unchanged, while the background seems to sort of shrink or grow. And this effect was developed by the cinematographer Erman Roberts for Alfred Hitchcock's 1958 film Vertigo. So what the Vertigo effect is actually doing is it's changing the relationship between the field of view of the lens, as in how wide the lens is, and the distance between the camera and the object that is being focused on. So for example, as the camera moves closer to the object, the field of view gets wider, and so therefore the zoom or the magnification gets smaller, so the object is staying the same size, but the background appears to expand and occupy more of the visible scene. So, whilst Andre Bazin was using surrealist photography as his example for this alternate reality that photography creates, when we discuss the Panofsky reading, we can also see how for Panofsky, perspective is something that has a strange relationship to realism because it's also very abstract. And for Panofsky, perspective operates as a system of symbolic meaning rather than simply a realistic recreation. So for another artist that you might be interested in, I've just popped in a few images of Julie Maritu's work, originally born in Ethiopia. Maritu is famous for her quite sort of fantastical spatial creations that use combinations of perspectival space with a kind of chaotic recombination of architectural diagrams or these sort of vector lines or a kind of, chaotic explosion of spatial construction in image making. And if you're interested in Julie Maritu's work, I thoroughly recommend researching her practice further. Okay, so this brings us to the end of the lecture. And now in our live discussion, I'd like our reading leaders to, first of all, tell us what is the historical context of the invention of perspective and why was this important for Panofsky? What does Panofsky say about perspective and perception? And why is perspective considered a symbolic form by Panofsky? Okay, so that's it for the lecture, and I look forward to our discussion in class. Thanks everyone. Bye-bye.